So we're going to discuss today about problems of oversensing. Okay, Hugo Pierre, you're here. What do you think about this plot?
Right. Well, we see initially it's a CRTD with two zones program, one VT and one VF zones, and we see an episode type VT. So we see an acceleration, V acceleration, and then well. Can I see the EGM? Or?
Yes, I will show you the EGM, but briefly you see that it seems that there is a dissociation between the ventricle and the atrium, and then you see that it seems that there is an acceleration in the VT zone, then 3 bursts are delivered, then 3 ramps, then 1 shock. It's a 10 joule shock, and what happens then?
And then it's probably degenerates into VF.
Yep, and then 1 maximal shock is delivered.
And then there's restores normal rhythm.
Yes, it seems that at the end there is a restoration of the normal rhythm. Okay, so now if you click on the EGM, please. So initially, you see, we're going to be very brief on this. Just after, it seems that there is an acceleration inside the VT zone. So a first therapy burst, and then a second burst, and then if you go up to the end of the episode, and the first shock, if you don't mind. So that's a real episode of VT with 6 initially anti-tachycardia pacing sequences, and all these ones are inefficient. And you see that, stop here, you see that what was programmed in this patient was a low amplitude shock, a 10 joule shock. And what is the effect here?
Well, it degenerates into VF.
Yeah, and so if just after, okay, degeneration into VF, and then a maximal shock will be delivered. But if you have a close look to the tracing, you see that the VF is ugly.
Yeah.
You see very, very polymorphic, very, very fast cycle. So I wanted to show you this first tracing, and then I will show you another one. But just to explain that, you see that with an ICD, of course, you can save the life of the patient. You see here, with a maximal shock, you can save the life of the patient, but the previous shock, 10 joule shock, you see that you can also induce life-threatening arrhythmia. And that's something that you need to be aware when you implant an ICD. Of course, you can save the life, the patient, but also with the same therapy, means an electric shock, you can also induce life-threatening arrhythmia. And that's something you need always to remember. In this patient, for example, he only demonstrated episode of stable ventricular tachycardia that were not life-threatening, but we have programmed a low amplitude shock, and we can of course discuss about the opportunity to program this kind of amplitude. But from this, you induce ventricular arrhythmia. And always remember that what you will induce with an ICD, most of the time, the VF that you will induce with an ICD are very fast, much faster than any spontaneous ventricular arrhythmia. In most of the cases, very polymorphic. And in this case, really, you need to this electric shock, because if not, then the patient will die. So remember, anytime you implant an ICD, you can save the life of the patient, but of course, you can also induce life-threatening arrhythmia. So I will now share my screen. And another example of this, you see here the tracing. What do you think here?
Okay, so you see an AV dissociation with an acceleration of the ventricle.
Yep.
One first burst.
Yes, one burst here, and then It's it's in the fast VT zone probably.
Yeah.
Okay, 3 zones have been programmed, whatever. One arrhythmia here, one ATP, no effect on the arrhythmia. Then one maximal shock is delivered, and what happens?
And then it degenerates into VF.
Yep.
And it doesn't work until the 5th shock, where there's a restoration of the normal rhythm.
So are you surprised about that? So if you observe that, are you surprised to observe that?
No.
Okay, you see, that's the problem with the ICDs. The patient who have the higher risk of induction of ventricular fibrillation are also the patient who have the higher risk of non-reduction with maximal energy. This is the concept of upper limit of vulnerability. It means that if you induce an arrhythmia with a high amplitude shock, then there is a direct relation, and there is a very high risk that you will not reduce the arrhythmia, that you have a high defibrillation threshold. Okay, so if we come back to the tracing, so initially there is clearly, this is the actual channel, the ventricular channel, so monomorphic ventricular tachycardia, fast, in the fast VT zone here, the first ATP is inefficient, and then one shock will be delivered, and this shock will induce the ventricular fibrillation. Okay, so it's not a very stable clinical situation, of course, is in quite fast VT, but from this quite stable situation, the electric shock induces a very unstable situation, clinical situation, life-threatening situations. And if you induce an arrhythmia, you always have to remember that there is a huge risk that you will not reduce the arrhythmia with the same energy. That's the concept of upper limit of vulnerability. So these two first tracings are there to explain that when you implant an ICD, if there is a high defibrillation threshold, not only there is a high risk that you will not reduce the arrhythmia, but there is also a high risk that you will induce arrhythmia with an electrical shock. So in these patients, of course, with high defibrillation threshold, you need to consider first the thing, should we implant this patient or not? Because there is a huge risk of induction of life-threatening arrhythmia. And in this patient, you want to avoid, and that's going to be the subject of today, the problem of inappropriate shock. It's a huge priority in these patients. You need to avoid inappropriate shock, because if there is an inappropriate shock, then there is a high risk of induction of arrhythmia, and then a high risk of non-reduction. Okay, and since today we do not test, at least in our center, the defibrillators, we do not know if the patient has or has not high defibrillation threshold. Therefore, it's a high priority for all the patient, of course, to avoid as much as possible the number of inappropriate shock. Okay, so the subject today will be the problems of oversensing. So what do you think here, Hugo Pierre?
Well, single chamber ICD with 2 zones program, 1 VT, 1 VF zone. And we see a classic pattern of railway.
Yep. Yes, you see these 2 lines here, and
looks like oversensing.
Yes, the sum of these 2 intervals equal this one. If the sum of this plus this equal this one, and this is very likely that this will correspond to a problem of oversensing. Which kind of oversensing?
T-wave oversensing.
T-wave or P-wave or double counting of the R-wave. When you look at the intervals, probably that this interval is too long for R-wave double counting. Okay, so it's very likely that it can be either P-wave oversensing with a long PR interval or T-wave oversensing. Okay, but you see the typical pattern here, railroad track here, and the sum of this plus this equal this. Okay, if you have a look to the EGM and show us after, see, Obviously, there is T-wave oversensing here. You see that the succession alternance between two signals, one sharp, one smooth, one sharp, one smooth, with oversensing of the T-wave. Okay, is this a difficult diagnosis?
No.
No, and that's a point. That's easy to do, and if it is easy for us, it may be also easy for the device to differentiate these two signals. Okay, because one is sharp, one is smooth, and that's going to be how works the algorithm, the Medtronic algorithm. What is always surprising is that when you compare the different manufacturers, there are manufacturers where they never encounter problem of T-wave oversensing. In Boston Scientific Devices, it's very, 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 very infrequent. Very, very infrequent. I have seen only one case in all my life of T-wave oversensing with a Boston. It's about the same with Microport. It's very infrequent. And that's not infrequent in Medtronic and in Abbott devices. And since it's not infrequent, they have tried to find a solution to this kind of problems. So now if I share my screen, what do you think here? So this is the first patient, and you see here this tracing, the same. You see the typical aspect.
Yeah.
And you see here, obviously, T-wave oversensing.
Yeah.
Okay. But what happens now on this tracing? So I'm sorry, it's written in French, but what do you think here?
Is the same tracing, or
it's another same patient, but another tracing? Okay. The patient was implanted in primary prevention. Okay, never experienced any ventricular arrhythmia. He was implanted, and after 2 months, he came back for electric shock.
Okay. Well, this looks like a real episode of VT.
On the plot, it's not obvious. At least there is an acceleration, a burst,
maybe dissociation, burst,
and then
an acceleration,
and then one electric shock. Okay, so now if we have a look to the EGM, you see here. So what happens? The numbers are numbers I have added to the tracing, but what happens here?
It's still T-wave oversensing.
It is clearly T-wave oversensing. Yeah? You see here the alternance between one sharp, one smooth, one sharp, one smooth. Okay, this is classified as a VF. You see, some cycles are in the fast VT, some cycles are in the VS. Okay, at this time, the counter for the VF is full. Okay, so you have a look to the 8 life cycles. There is at least one here, which is FS. So it's classified as an episode of VF. Okay, so what happens then?
Then there's an ATP.
ATP, the rate of the ATP is based on what?
It's based on the interval of the
the last 4, it's going to be last 4, whatever, but it's based on the supposed intervals of tachycardia. But you see here the real ventricle are there, but the device considers this is also an arrhythmic event. Okay, so what happens here?
And then there's an ATP. Well, it starts in the T-wave.
Yes, the first bit is delivered right on top of the T-wave. Okay, so what happens then?
And then it degenerates into
and you see once more very fast cycle. It's very infrequent to see. It's not impossible, of course, but it's at least infrequent to see these very short cycles at the level of the ventricle in spontaneous arrhythmia. But this is not infrequent when you induce an arrhythmia with the defibrillator. So this patient was completely stable without any episode of ventricular tachycardia or arrhythmia before implantation. You implant the device, T-wave oversensing, and then the first bit is delivered on the T-wave, and you induce a very fast and polymorphic arrhythmia, okay, and a life-threatening, okay. Luckily, this patient has not the night thresholds, so at the end, the shock which is delivered is efficient with reduction of the arrhythmia, okay. But remember, T-wave oversensing must be considered as an emergency, because if in case of T-wave oversensing, you receive either an ATP sequence or an electric shock, there is 50% of chance during, if you receive an electric shock, that the shock will be delivered on the T-wave, okay? Because you will try to synchronize either on the T-wave or on the R-wave. And if you deliver a shock on the T-wave, if the patient has a high threshold, then you may induce an arrhythmia. Or if you pace on the T-wave, you may also induce an arrhythmia. And if you have a high threshold, you may induce an arrhythmia, and then you may not reduce the arrhythmia. That's why a T-wave oversensing can be, in some situation, in patient with high threshold, needs to be considered as real life-threatening situation. Okay, this kind of tracing explain why, according to the way you will program the device, in some situation, you may have a direct impact on the mortality of the patient. Okay, so remember, when there is a situation of T-wave oversensing, if you don't know if the patient has a high threshold or not, you may consider this patient as a life-threatening situation. Okay. In this case, you see the patient, but if there is a high threshold, and if you induce an arrhythmia, you may not re-see the patient again, and you may not see the tracing of the death of the patient, so you may not know that that was the problem. But I don't think that this is very infrequent, this kind of situation. Okay? No question? So what do you think here?
Now we have the same railroad track pattern, and the device classifies it as T-wave oversensing.
Okay.
And so it withheld the detection.
The railroad track is not obvious here.
No?
No.
Okay.
So the intervals are very close. This is a problem of T-wave oversensing, but sometimes the T-wave is just in between the two R waves. So the RT and the TR interval may be quite similar. Okay, so and what is the diagnosis here for the device?
T-wave oversensing.
Yeah, so if you click now on the EGM, you see here, the diagnosis is based on the tracing on top, on bipolar, okay? Mm-hmm. This is the shock channel without analysis here. And you see, if you see just a bit after, you see the problem of the T-wave oversensing, obvious, and then go just to the diagnosis. Okay, up, you see here the marker T-wave. So as I had tried to explain, the diagnosis of T-wave oversensing is obvious for us. If during an exam, I give this tracing, 100% of the students will find the diagnosis of T-wave oversensing, because it's obvious. Visually, you see immediately that there are two different signals and that there is an alternance between two signals and two intervals, one RT, one TR, okay? And since Medtronic had this kind of problem, they have developed an algorithm, and this algorithm will help the diagnosis of T-wave oversensing. And if there is a diagnosis of T-wave oversensing, once the counters are full, then the therapy will be suspended, will be for this, no therapy will be delivered since there is a diagnosis of T-wave oversensing in the VT zone and also in the VF zone, okay? I think that this algorithm works pretty well, I would say. Okay, in the case we have seen, that's surprising to me that there are still problems of T-wave oversensing in Medtronic devices. I think they should correct that, because all the other competitors in Biotronic in 5 or 10 years ago, there were many episodes of T-wave oversensing, and that the problem has been solved. I have the impression that in Abbott devices, we have less now episode of T-wave oversensing, but there are still some episodes. In Medtronic, they still need really to correct that. And it's not so frequent in spontaneous activation, but it's quite frequent. Frequent is not the good word, but we see many cases of T-wave oversensing after ventricular pacing. The impact on the patient is not the same because no shock will be delivered in this case, but I think that could be corrected. So you see here, there is an algorithm which is based on this idea of two different signals, one sharp, one smooth, and with stable intervals. The RT are stable, and the TR intervals are also stable. They can be the same, RT and TR, like in this example, but they need to be stable, okay? So the repetition of these sequences of T-wave sensing, and then no therapy will be delivered for this episode. If you click on the parameters, you see here, detection V, if you click, yep, no. You see, the T-wave is on, and this is the algorithm here where you can program it. Okay, if you come back to the tracing, can you come back? If you click back on the tracing. Okay, what is the problem in this patient? What do you think is the problem?
Well, the bipolar channel is the amplitude of the signal is very small.
Yeah, that's the problem in most of the cases. In most of the cases, not all, but in most of the cases, the problem of the T-wave oversensing is a problem, in fact, of R wave. You see the very small amplitude here of the R waves. If there is a small R wave, small amplitudes, then the device will work with the maximal sensitivity all the time. Okay, if it is programmed 0.3 millivolt, then it will work more or less during all the cardiac cycle at a 0.3 millivolt with a very, of course, an increased risk of oversensing of the T wave. Okay, so in this patient, with the algorithm, no therapy is delivered, which is a good point. There is T-wave oversensing, but no inappropriate shock is delivered. And that's crucial, as I explained before. In patients with T-wave oversensing, you need to avoid electric shock, because if the shock is delivered, there's 50% chance of the shock being delivered on the T-waves. And if there is a high threshold, then a huge risk of induction of ventricular fibrillation and a huge risk of no reduction. So this algorithm helps to avoid the delivery of electric shock. But what would you do in these patients?
We could change the lead configuration to integrated bipolar.
Yeah, exactly. If you close, you see in the parameters, you see the level of sensitivity, it's 0.6. Nominally, it's 0.3. So I think it has been modified. I'm not so sure that's a very good idea. If you measure the signal, the R wave is very small. So if you degrade the sensitivity, of course, you will reduce the risk of T-wave oversensing, but you will considerably also reduce the possibility of correct detection of a real episode of ventricular fibrillation. And that's the first task of a defibrillator. A defibrillator, you need to correctly detect ventricular fibrillation. If you do not detect ventricular fibrillation, there's no point to have an ICD. Okay, so in this situation, that could be a problem. So if you click on pacing, and you see that's, I think that in Medtronic devices, you have more risk to have T-wave oversensing, but you have an advantage compared to all the other competitors, is that you can modify the sense polarity. If you click on it, you can program it to tip to coil. That's a specificity for Medtronic device. If it is a real bipolar lead, of course, if it's not a Boston device lead, if it's a real bipolar with two electrodes at the tip of the leads, and then you can select the sense polarity and you can change it from bipolar to tip to coil, okay? And if you program it tip to coil, then you will modify the vector of a sense of detection. And in some situation, you may solve the problem. So I will show a tracing in this patient. Yeah, you see here, so I'm sorry, it's French, but this was the case of a patient with T-wave oversensing. Initially, R wave, its program in bipolar is 1.3 millivolt. So with this kind of sensing, you may encounter risk of oversensing. The more the smaller the amplitude of the R wave, the more you will work with very high sensitivity. So the more you will increase the risk of any kind of oversensing, 50 hertz, I don't know, my potential, any kind of oversensing, T wave, P wave, R wave double counting. And it was this case in bipolar. And then we have modified, you see, the parameters to distal spear, so tip to coil, okay? This is in French, and you see here the considerable increase in the amplitude of the R wave. And now, if you look here, the R wave, before programming, you see, very small R wave. And in this kind of situation, that's a huge problem because you're not sure that you will correctly detect an episode of VF, and you increase considerably the risk of any oversensing. And once you have modified the programming, you see now that you're working with a device with 8 millivolt of R wave. And in this patient, there was not anymore any problem of oversensing. And I think that in this situation, you increase considerably the risk to correctly detect an episode of VF. Okay, so it is not systematic. It's not like with pseudo bipolar sensing, the amplitude is increased compared to bipolar. We have studied more than 100 patients, and at the end, the average value was the same with bipolar and with pseudo bipolar sensing. But patient by patient, sometimes there were huge differences in one configuration and in the other one. So if you encounter a situation with a low amplitude sensing with bipolar, you may try pseudo-bipolar programming in Medtronic devices, and you may solve situation. In normal situation, I remain with bipolar sensing, because when you discuss with Medtronic engineers, they explain that all their ICD has been tested and all the algorithm has been built with bipolar sensing. So they are not too confident if you program this pseudo-bipolar. But in this specific situation here, if you do not do that, then you will need to change the lead and replace the lead somewhere else, because you cannot work correctly with this kind of sensing with 1 millivolt on this. So in this situation, we could avoid the fact to change the lead. Okay. Okay, so if we conclude on a T wave, it can be an emergency. Be careful in patient with high threshold. You may have a life-threatening situation. In many situations, there is a problem of small R wave. T-wave oversensing is in fact a problem of small R wave. So you need to program the algorithm to avoid the delivery of inappropriate shock, but then you need to consider on how to improve the quality of sensing. And one of the possibility is to reprogram to pseudo-bipolar sensing. Okay? No question about T-wave oversensing? Nope. So now a case of, you see this patient, that's a patient that was lost to follow-up. In our centers, all the patients are followed with remote monitoring, but not this one for one reason, and he didn't want to come back. So we have not seen this patient for years. And he came back for many, many episodes of electric shock. And if you see the curve here, there is an increase of the pacing thresholds, there is an increase of the impedance, and there is also a decrease in the R wave amplitudes. So these signs are not are quite late in. This is a patient with an obvious lead dysfunction. We're going to have a look to the tracings, but this is quite infrequent now. If you with all the algorithm and with remote monitoring, you can avoid these kind of terrible situations. And most of the time, we see the problem of lead dysfunction way before the increase in threshold, way before the decrease in the T wave amplitude, in the R wave amplitude, and also most of the time we can see it before the modifications of the pacing impedance. Okay, so if you have a look to the tracing, so this one, you see here, what do you think about this?
very disorganized
Yep.
intervals in the VF zone and also in this, slow zones. So this looks like lead failure.
Yeah, and you see this cloudy situation, many points everywhere, but there are also very short cycles at the level of the blanking.
Yeah.
Okay, you see, and when you have both this is very, very unlikely that this is physiological. This looks like one of the diagnoses is the problem of lead dysfunction. Okay, and you see in this situation that the patients received 6 electrical shocks. In Medtronic devices, for one episode of VF, you can only receive 6 electrical shock, and this is the reason why, because you could program more, but if it is inappropriate, I think it's better that you stop after 6 electrical shocks. If you click on the EGM, not here. So if you come back, yes. Alors, où tu étais exactement? Vas-y, montre-moi. Non, il y a le N. Là. Okay, you see here. You see, obviously, it's unphysiological, the signals that you see, and that was a problem with a lead failure, for sure. Just I show you this tracing, but you see the marker N. There is an algorithm which is designed to avoid the inappropriate therapies in case of lead dysfunction. We're going to rediscuss it in another tracing, but as I said before, the one about T-wave Oversensing is working pretty well. I've not seen any inappropriate therapy on T-wave Oversensing since we programmed this algorithm. In contrast, this algorithm about noise is not so efficient, and that's an example here. You see that initially there is a diagnosis of lead dysfunction of noise, but at one time, there is no diagnosis anymore, and then the shocks are delivered. Okay, it's not a question of clock here. You know that you can program a clock. If after a certain time there is a diagnosis of lead dysfunction, it will deliver the therapy. That's not the case here. That's just a limitation of the algorithm. But you see here, okay, the situation, you see the signals, and that's something I hope we should avoid now, this problem of inappropriate therapy, repetitive inappropriate therapy. Here it's quite obvious here. You see unphysiological signals. I don't know how to say it, but do not move up here. You see these signals has been clipped because of high amplitude. That's a problem of probably lead dysfunction, no doubt about it. Okay, so that's an induction here.
Okay.
At the end of implantation,
okay.
See, induction. What happens?
And then we have an acceleration that is organized in the VF zone, and then the shock probably just terminates the lead.
Yeah, you see, this looks like a physiological arrhythmia.
Yeah.
Possible, and this looks like a lead dysfunction.
Yeah.
Okay, so if I show you the tracing, you see here induction, detection. One shock is delivered, and after that there is a reduction of the arrhythmia, but you see here these signals, very huge amplitude signals, and that's clearly a problem of lead dysfunction. And you see the difference between the signals, that absolutely no doubt. It's not so difficult to diagnose also. Okay, so we expect that really it's going to be possible to differentiate this from this. Of course, you are in the VF zone, so you need to be careful. If you say this is not a real arrhythmia, you need to have 100% of specificity and sensitivity here, okay? Because you don't want to not deliver a shock if this is a real ventricular fibrillation. But what happens here is that the shock delivered reveal the lead dysfunction. Okay, before that, the impedance was normal, and we have never seen this kind of signals, but this, we changed the box of the device, we retested. This was a specific lead, this was a Fidelis lead, and this Fidelis then really reveal the lead dysfunction. Okay, but once more, on the plot, it's obvious. that take quite a for every tracing. I take quite some time to have a look to the plot, always to start with, okay, with the analysis, because here you can have the diagnosis, this and use a real probably arrhythmia, and then this looks like it's very unlikely that this is physiological. Okay, vas-y. So as I explained, there have been some problems with Medtronic leads, the same for Abbott, and these two companies had to develop specific algorithm to avoid inappropriate therapy. The very first one is the LIA. How does it work?
Yes, it's based on 3 parameters.
Very simple. The LIA is a magical algorithm. It works very well, very, very well to avoid. If the patient is followed with remote monitoring, really, with this algorithm, you will decrease considerably the risk of inappropriate therapy. It's a very simple. The situation we could discuss about it, how it was developed, but the situation was a huge problem with Medtronic, and they had to have the possibility to integrate this algorithm in the new devices, but also in the old ones. Okay, and they have done something with very simple parameters, and I really believe that it works pretty well. So, what is the concept here?
If I remember correctly, it will trigger an alert if there is 2 out of 3 abnormal parameters that are the normal lead impedance.
Yep. So I will not give you all the details, but the device will measure every day the impedance, and it will do the average value over 13 days. And then if one of the values the next day is more than 150%, 175%, or less than 50% of this average value, that's going to be one. So if there is a abrupt change in the value of the impedance. Okay. So that's the parameter 1.
The second one is 2 or more episodes of non-sustained VT with intervals near the blanking.
No, non-sustained VTs, it means at least 5 intervals with an average value of less than 220 milliseconds.
Okay.
So episode of non-sustained VT, at least 5 cycles with short cycles, but not so short. It's 220 milliseconds. Okay.
And the third one is the short VV interval counters.
The short VV interval counters. Okay, at the level of the blanking this time. If you program a blanking of 120 milliseconds, a short cycle is cycle of 130 or 120 milliseconds. Okay, and if you have 30 of these short cycles one day on 3 consecutive days, then it's going to be also a positive factor. Okay, so you need 2 out of the 3. So abnormal value of impedance, short cycles at the level of the blanking, or 2 episodes of non-sustained VT. And if you have a look, in the cases of lead dysfunction, most of the time, the 2 parameters are the short and the non-sustainability, not the impedance. You see, if you base all your strategy about preventing inappropriate shocks with remote monitoring, and you only have the measurements of the impedance, you will have quite late diagnosis. The short cycles and the non-sustainability, they are not in all, but in most patients are encountered before the problems of impedance. And if you see these 2 out of 3, you will not inhibit the therapy. You will just delay the therapy. So if it is not programmed on 30 out of 40, the initial counter for the VF, then it will automatically be programmed on 30 out of 40. And you will also alert the patients, either with the noise or with the remote monitoring, with both of them, in fact. Okay, every 4 hours. Okay, so the idea is not to inhibit the therapy, but just to delay the therapy and to alert. Okay, and as I said, there is a second algorithm which is supposed to be complementary. You see here, what you see here, it's V oversensing noise. If you show us the EGM, and okay, it's based on the comparison. I will not go too much into detail between the bipolar channel and the shock channel. See, most of the time, not most of the time, but in a lot of time, there is oversensing in one of the channel and not in the other one. So you will compare the channels bipolar and say, okay, there is noise in the bipolar and there's no noise. It's not exactly like it's based on the amplitude of the signals, but whatever. And if there is a dissociation between the two channels, then you will arrive to diagnosis of noise, and then you will inhibit the therapy for these episodes. Okay. Once more, to write this and to collect these cases, I have tried to find cases of T-wave oversensing. Once more, in all the patients with T-wave oversensing, the algorithm worked pretty well. In this case, it was not so obvious. I have seen not many, but some cases at least of first diagnosis with the noise, and then at one time the therapy is delivered because no diagnosis anymore of noise or sensing. But this one, this algorithm of noise require that the counters are full. Okay, so you need 30 out of 40. So the LIA is positive way before. So if you work with the LIA and remote monitoring, in most of the situation, you should not have to need this algorithm, this second one, because this one it will work once the counters are full. And once more, the idea of detecting and preventing inappropriate therapy is to arrive to the diagnosis of lead dysfunction way before you counter are full. The only situation, it's not the only, in most of the time it works correctly. And in our centers, it's now I will say never encounter situation of inappropriate therapy in case of lead dysfunction. The only situation is the one we have seen before, when there is no signs of the dysfunction, one electric shock, and then complete failure of the lead after, and then inappropriate shocks. In this case, the LIA may not work correctly. Okay. Any question on that?
So we probably have an atrial arrhythmia, and the ventricular cycle alternates between slow and VF zone.
Yep. And here?
Here, well, it's stabilized for a few cycles.
Yep. But it seems to be the same rate that the action. Surprising. Okay. So now I'm not sure about the diagnosis, just with the plot here. Okay. So now if you have a look to the tracing.
So we clearly have an atrial arrhythmia on the atrial channel.
Yes.
With yes, and then we have.
You see the prints of the atrial signals inside the ventricular channels. The first one are not sensed. Okay, but what happens here?
Yeah, it's sensed in the ventricle.
It's oversensing of, the atrial signals inside the ventricle. Why this one is sensed and not this one, for example?
Well, the amplitude seems a little bit.
Oh, no, it's systematically this one.
Okay.
There is an increase of the sensitivity along the cardiac cycle. It's adaptive. You start at the percentage of the RWA, but then you will increase the level of sensitivity. So, of course, there's more chance to oversense this one than this one or this one. Okay, so this is atrial activity oversensing, and then what happens?
And then
the good point here is that since it's adaptive, anytime you sense here, and then since the patient is non-dependent, there is a ventricular spontaneous activity. And if there is a ventricular spontaneous, anytime the sensitivity will readapt to the level of these signals. Okay. Here you see that there is no ventricular activity, spontaneous activity here. And that's why when you are pacing dependent, if you are in complete AV block, you increase considerably the risk of prolonged oversensing. Okay, because if there is a spontaneous activity, ventricular, then you will readapt to this. But you see here, For any reason, there is no ventricular activity here. And since there is no ventricular activity, there is prolonged oversensing, because here you will work to very high level of sensitivity here. So you oversense this one, this one, this one, this one, this one. By chance, there is a ventricular activity. If not, then you will have a prolonged oversensing. That's also something you need to know. A patient who is pacing dependent, if there is problem of sensing of this kind of problems of myopotential, of diaphragmatic myopotential, or atrial activity oversensing during atrial arrhythmia, then there is a risk of very prolonged oversensing. And in these patients, you can faint because of bradycardia, and then you can receive an electrical shock. Okay. By chance, there is once more 1 hour with correct sensing, and then you readapt, and then you do not sense this one and this one. Okay. So, in which situations do you encounter this kind of problem? Problem of P wave oversensing or atrial activity oversensing?
Could be that the lead is too close to the tricuspid annulus.
Yes, that's the main reason. If you place the lead just after the tricuspid, then you may. And which kind of lead, according to you?
Integrated bipolar.
Yes, the one, most of the time, if you see these kind of tracings in any books about ICD, it's going to be a Boston device, because the rate of this kind of oversensing is much higher in case of pseudo-bipolar leads. You will sense between the tip of the lead and the coil, and if the coil is placed on the tricuspid or too proximal, then you increase considerably the risk of P wave oversensing. So that's also something. Any manufacturers will have different problems. In Boston, you will never see T wave oversensing. Not never, but nearly never see any problem of T wave oversensing. But you may encounter problem of P wave oversensing. That's the other way around with Medtronic. You will see T wave oversensing, and if there is a problem of P wave oversensing, it's not all the time, but most of the time it's because you have connected a bipolar, pseudo bipolar lead, a Boston lead. Okay. Okay. The lead may have moved also. You implant the leads, then it moves. And if the lead has moved and it's at the limit between the atrium and the ventricle, you may find these kind of situations. But most of the time in this situation, the amplitude of the R wave is very variable, the lead that's moved. Here in this situation, the lead is placed just after the tricuspid and the R wave is stable, but you may have problems. One other very infrequent situation is sometimes you place the lead inside the coronary sinus. You don't want to, but for any reasons, you've placed inadvertently the lead inside the coronary sinus, and then you will also sense the atrial lead, the atrial signals. And more infrequent is when there is a contact between the atrial lead and the ventricular lead. Sometimes you may see also P wave oversensing. And the last situation was with the Abbott lead. You know, the Abbott lead, there were problem of also of lead dysfunction. Mm-hmm. And most of the time, the problem was initially at the level of the atrium. So the very first signals that you could see in this situation were problem of P wave oversensing, then R wave oversensing, and then in the appropriate shock. Okay. Any question? Maybe one last tracing. What do you think here? So normal, initially normal rhythm, yeah, and then acceleration in both the ventricle, yeah, and the atrium. Okay. Yeah. So what do you think here? What could it be?
Maybe an oversensing.
Something oversense, probably. Yep.
External noise or something like that.
Yeah, yeah. You see here, typical external noise. Okay. Both at the level of the atrium and the ventricle. It's in France, so it's a 50 hertz. I think it's 60 hertz in US, but 50 hertz in France. You see, you have not the possibility to change here the I don't know, the speed of the tracing. You see, yeah, it's 25 millimeter by seconds. In other manufacturers, you can change, you see, the speed. And if you can change, then you don't say, I think it's 50 hertz, you measure it. If you change the speed of the tracing, then you can clearly measure and see that's clearly 50 hertz. Okay, and you see the concordance between these two, between all the channels. Okay, remote monitoring is determinant in this situation. If you receive an alert for that, you can ask, what were you doing? You can ask the patient, what were you doing exactly yesterday at this time of the day? And most of the time you will remember. If you see the patient on face-to-face after 3 months, and you will ask him, what were you doing exactly in August, the 3rd of August, he will most of the time not remember. So it helps for the diagnosis, the remote monitoring also. And okay, okay, no, nothing else. Anything to add or any questions? Nope, nobody. Okay, so I think we're going to stop there, and we'll next week, it's going to be the last about Medtronic. We're going to discuss about discriminations. So see you next Monday for discrimination of Medtronic ICD. Bye.